Alrighty, CNT140, we're looking at Chapter 7 on fiber optic termination and splicing. So we're going to look at different connectors, different methods of terminating those connectors, different splices, different types of splices we can use to repair fiber, if you will. So let's dig in. Fiber optic terminations come in two categories, either putting a connector on the end or splicing together either two fibers, or splicing on a pigtail that actually has a connector on, factory finished connector on. Connectors themselves are basically a temporary connection that I can plug and unplug. Think of like a patch cable. Meanwhile, a splice is a permanent joint between the two fibers. Again, if I'm dealing with two long fibers that I'm joining together, I'm going to splice those together. That way they're basically a permanent connection between the two. Either method must have two primary characteristics. Good optical performance, meaning there's not much signal loss going from fiber to fiber or connector to connector. And also high mechanical strength. We don't want that to be the weak point and when I'm moving cables around or connecting or disconnecting things. The right style needs to be compatible with the equipment and also protect the fiber from the environment, whether it be water or dirt or whatever. Those terminations need to be protecting the fiber from those elements. Connectors over the years have been given a lot of attention. Manufacturers come up with well over 80 different styles of connectors, a dozen different ways to install. So as we get to the connector part, we'll talk a little bit of history, but then we'll talk kind of the common ones you would encounter, the common ones that get used, especially now. Splices, there's pretty much two different ways to do that, but a number of different ways to actually implement them. And again, out of all of these, we'll talk about kind of the common ones that come to the surface. Multi-mode fiber is relatively easy to terminate. We're actually going to do that in the lab room. Field termination is generally done by installing connectors directly onto the tight buffered fibers. Again, that's kind of what we're going to do in the lab room with you. Single mode fiber, it requires extreme care, and it's usually done in either a clean manufacturing plant or a clean truck at maybe a job site where you basically have a clean room in the truck. Field terminations are usually done by splicing on a pigtail that has a factory installed connector on the end, if you're going to do that, or it's bringing the two fibers into the truck in a clean environment and splicing them together. Choosing a connector, I need to make sure it's compatible with what is being used equipment-wise, so forth. You can actually get cables, either made or make cables that have one style connector on one end and a different style on the other end, in case you are upgrading systems. I need this currently to work until we can upgrade or whatever. That can be done, but I do need to think connector compatibility. Is the termination process familiar to the installer, or is it something new that training needs to occur? And is this connector acceptable to the customer? Maybe the customer has something new in mind and you might need to maybe educate them on this is the common one used. Or maybe they have equipment that are like, well, no, this is what we actually currently use. This is kind of the connector we would like to use for this site. Splices are considered permanent joints, and you can either do fusion splice or mechanical splice. Fusion splicing is probably the most widely used. It provides, in some cases, almost like zero loss, if you will. As we do our terminations in the room, you'll see that they call it practically zero loss when those are terminated. Virtually all single mode fibers are fusion spliced. Mechanical splicing can be used for either temporary restoration or some multi-mode splicing. You can use a mechanical splice, and we'll look at examples of those a little bit later. The primary specification for connectors or splices is the loss, the amount of light that's lost in the connection. And we're really talking about connection loss, the loss of the mated pair of connectors or the two fibers coming together, and that's expressed in decibels. Measure of loss of the connectors, you must mate them to a similar known good connector to be able to actually measure that. But the measurement of, the quality there, if you will, is the amount of loss that we have as light is moving from fiber to fiber or from connector to connector. Only the light that actually makes it into the core of the receiving fiber will actually get transmitted, propagate. The rest becomes loss. So I always think about taking two garden hoses and putting them together, maybe holding them right next to each other. And if I get them really well lined up, most of the water makes it from one hose to the other one. You get a little bit of water squirting out. That's your loss. That water squirting out is the loss. If I have them badly aligned, I might have water spraying everywhere. That would be a lot of loss. So kind of think of, taking two garden hoses and trying to join them. If I have a good solid connection, I have very little loss. That's kind of one way to think about this fiber alignment and so forth. Connector and splice loss caused by a number of factors, and this loss is minimized when the two cores are identical and perfectly aligned. Just like I said, there's two garden hoses, same size and perfectly aligned. There should be zero water squirting out, if you will. And secondly, the connectors or splices are properly finished and no dirt is present. So polished, if you will, no oil and dirt on them, and I should have, maximum signal from fiber to fiber. Now, problems can occur that will cause loss. And so they're going to talk about a couple different problems that can occur that will cause signal loss. End gaps, a gap from one, think about this as one connector to another connector or fiber to fiber. If I have a gap between them, just like having two garden hoses, that water is going to start to pour out or spray out. And this is called insertion loss and reflectance. Actually, two problems of end gaps cause insertion loss or reflectance. This would be insertion loss, where I literally have a gap there and think about water spraying out and not making it to the other hose. The other loss is reflectance. Reflectance is literally light as it's moving from fiber to fiber. As the light leaves the glass fiber and hits the air, there is a difference in index of refraction between the fiber and the air. So that is actually going to cause the light to spread out, if you will, and not make it into the other fiber. Some of the light will do that, not actually make it into the other fiber, try to bend out of the way. And that is going to cause some signal loss. The other thing we have, optical return loss or reflectance can happen as well. Connector using a number of polishing techniques to create convex fibers to ensure physical contact. So you can actually get those two fibers touching each other. So we have, again, two garden hoses touching each other, trying to get maximum light from one fiber to the other one. If you have any kind of dirt or oil in there, that can cause the signal to maybe, get absorbed, if you will, as hitting dirt, or actually hit something and reflect out and not make it into the other fiber. Rough surface will scatter light. Dirt is going to scatter or absorb. If they're not terminated, when connectors are not terminated, you should be putting dust caps on to protect them and not touching the end of the fiber, oils, and so forth. And actually, before connecting, we should be cleaning the connectors, just like we did in the lab room. When we hooked up our fiber links, we carefully cleaned the end of the connector before we plugged them in, trying to get rid of that oil and dirt that might cause loss. If I have mismatched fibers, whether it be core diameter or the numerical aperture, we're going to have loss. So again, think about two garden hoses, one that's larger and one that's smaller. When I join those two, the larger one has too much water for the smaller one, so the water squirts out. It gets lost. And that's kind of what they're trying to show you here. It's not actually making it into the fiber and actually tries to go to the cladding or bends out of the way and never even makes it. And here they remind you about connecting smaller fiber to a larger one. I have loss, but it's minimal. It's when I go from the larger fiber to the smaller one that I have substantial loss. And again, do the whole, large garden hose to small garden hose kind of thing. Typical connector losses are generally in the 0.3 decibel for factory polished single mode or multi-mode. Not many installers will do single mode fiber field termination. It's generally fusion splicing of factory-made pigtails onto the fiber. That's actually the kind of termination we'll do in the lab room. We'll fuse on a connector. Multi-mode fiber field terminations are common. That's actually what we're going to do. We're going to fuse on a connector from multi-mode.
The field termination pre-polished splice connectors using a precision cleaver can produce consistent results around 0.5 decibels. And we'll see that as we do our connections. TIA 568 calls for connection losses of less than 0.75 and splice losses less than 0.3 decibels. This allows for these pre-polished splice-on connectors to do that. We can have connector reflectance as well. This is when we have back reflection. As light moves from fiber to fiber, it hits this surface here, again, this air gap in this surface, and some of that light is going to reflect back. That is going to be in the form of loss. Some of it is not making it to the other fiber, and that can be a source of loss. Connectors then, minimizing this to get the maximum out of that, monomode fibers, this reflection is less of a problem, but more of a problem with your single mode fiber connectors. Single mode fiber connectors is a bigger problem with your reflectance. Ways they have adapted the connectors or modified the connectors to help reduce this. Well, this first one shows you the flat polish. As light leaves one fiber, hits the other one, some of it gets reflected back. The next step they did was actually polish the end of the ferrules here, slightly convex. And the idea is only the center of the connector touches the center of the other connector, trying to get those two cores lined up and directly touching each other. That is one way they were able to reduce this reflection. Another adaptation along the way is they did an angled physical connector. And if you look down here, it's a slight angle, just a couple degrees. And the idea there is, as one fiber touches the other, again, they're still touching, those two cores are still touching. Any reflected light, since it's a slight angle, will reflect back in an angle and kind of out of the core. So it's lost, but it's not, coming back at the original light source. So the overall loss is less. There's still loss, but the overall loss is less. Okay, styles of fiber optic connectors. All right, we will come back in the next podcast and start talking different fiber optic connectors.